सर चढ़े हमारा हालात
As you
खराब
people
भी कर रहे हैं
convenience here.
सर जाए इनको हाँ
Sir जान को yes,
बस उस चुप सही
बिल्कुल बिल्कुल.
मैनेजर से माइक थे आप साथ उस
जी अस्सलाम वालेकुम to everyone. I hope everybody is okay.
वालेकुम सलाम सर
वालेकुम अस्सलाम.
आप लोग ठीक ठाक खैरियत? अच्छा.
वालेकुम सलाम sir.
Okay, so welcome to this new session of applied econometrics. Let me tell you what's the agenda for today. Okay. Okay, so let me see. अगर आप में से किसी का माइक वो है ऑन है तो आप उसको म्यूट कर दें काइंडली. थैंक यू. Okay, I would start from a quick discussion, although the purpose is not to spend the whole lecture on this, but it's important to cover this portion as quickly as possible. In the last lecture, we had a discussion on the basic idea of the OLS method, which is the most frequently and most usual method of estimation in econometric models. This particular regression model that we are talking about, it is based on certain assumptions. These assumptions play a very important role later on when you want to determine whether your fitted model is a good model or not. Because as you know, whenever we talk about a model, we always associate certain assumptions with that model. The purpose of the assumptions in layman language is simple: to ensure that the model give you the desired results that you're looking for, right? So if those assumptions, in a sense, assumptions represent the properties pertaining to different features of the model. If those assumptions hold, then the model would give you the desired result that you're looking for. If some of those assumptions are not working and you still use the model, then you would get a model, but that would not give you satisfactory results. So therefore, whenever you are talking about an econometric model, or in that sense, a regression model, you should also take care of the underlying assumptions. The assumptions that I'm going to quickly discuss with you right now, these assumptions are initially considered to be true. By true, I mean you assume that they are working, okay? Later on, we then challenge some of these assumptions. We say, what if this assumption is not working? What if that one is not working? And then the whole subject of econometrics is the result of violations of some of the important assumptions.
Excuse me, sir. Screen, sir, वो नहीं है, disappear हुआ है. Visible नहीं है, sir, screen.
Okay, thank you. I just forgot. I'm really sorry. Interestingly, मुझे अपना screen नजर आ रहा है, तो मेरा ख्याल था आपको नजर आ रहा है. I'm really sorry for that. I will do it right now. Okay, sorry. I should have done that thing right at the start. Okay. So okay. Let me just see. Okay, is it visible right now? आप बताएं.
Yes, sir.
All right.
Yes, sir.
All right. Okay.
Yes, sir.
So the point that I was talking about was simply this: that whenever you talk about an econometric model, or for that sense, a regression model, this model is based on certain basic assumptions. These assumptions are initially considered to be true. By that, I mean you assume that they are working, they are holding. although it's not necessary that they would always be holding in real life, okay? But you know from your previous understanding that whenever we talk about a model, then initially we start with the assumption that this model along with its basic assumptions are okay. What's the advantage when we assume that initially the assumptions are working? The advantage is that the necessary derivation, the necessary results, I would say, necessary results which you get for the corresponding theory, they are very much dependent on these assumptions. So under these assumptions, you get some standard results for your model. As you would see some of these results, I would be actually telling you what are those standard results. So under these assumptions, when you develop a theory, you consider these assumptions to be working and you get some standard results, some standard derivations, some standard formulae, etc., etc. And then later on, as we would also do exactly in this course, we would say that how if this particular assumption is not working, then what you should do. Okay, so immediately after discussing the assumptions and getting some standard results, we will go for discussing some of the important violations of these assumptions, violations which you would really observe in real life, and there would be certain names for those violations, and they will actually constitute our different topics, right? So for example, you will be hearing from me something like multi-corinality, heterozygosity, autocorrelation, and some others. So these will be some of the topics that would be a direct result of the violations of the assumptions that I am going to present to you right now. But before we can go into that discussion, we would not put ourselves immediately into questioning these assumptions. We would say, okay, forget about whether they are working or not. Initially, we start with the assumption that these assumptions are true, right? So in regression analysis, our objective is not only to obtain the estimates of our regression parameters. In the last lecture, if you remember, we discussed how can you get the OLS estimator for the slope and the OLS estimator for the intercept, okay? But we would also go one step further. What is that one step further? We would draw inferences, okay? Inferences means like hypothesis testing. So it would not be enough just to get the numeric estimates of beta 1 hat and beta 2 hat. That's of course a very necessary requirement, because one of the steps of the basic methodology of econometrics, if you remember from our first lecture, was estimation of the econometric model. So estimation is of course a very important step, but if you estimate the parameters, like if you get beta 1 hat and beta 2 hat, the next step is to use this information to make statistical inference about the true values of the parameter, right? By true value, we mean the actual parameters. The actual value is beta 1 and beta 2, right? In the current notation, I hope you remember beta 1 stands for the slope. Beta 1 stands for the intercept, and beta 2 stands for the slope, okay? Like as you can see here, okay? Beta 1 is intercept and beta 2 is basically the slope. So we are basically interested in the actual values of beta 1 and beta 2. So once you get the numeric estimates of these two in the form of beta 1 hat and beta 2 hat, your next step is to generalize from the sample information to the whole population. This generalization from sample to population is given the name of statistical inference. Okay, so when we say we draw inferences, actually we want to generalize from sample to population, or what I usually say, you want to generalize from the small picture to the larger picture, because it is actually the larger picture in which we are interested, and using the sample is just a way of getting information about the larger picture. So therefore, your purpose is to determine how close the sample values of the parameters are to the actual values. So for that, you need statistical inference. And as you would see, in order to use the estimated model to say something about the actual values, there are certain assumptions related with this particular model that would play a very important role. So there are a set of 10 assumptions associated with the regression model. If any regression model which satisfy these 10 assumptions is given the name of CLRM, as you can see here on the slide, CLRM, classical linear regression model. Although people also give it other names like Gaussian linear regression model, right? Standard linear regression model, but usually the common name is classical linear regression model. So whether it's a simple regression model, which means only one X variable is there in the model, or whether it's a multiple regression model that we will discuss immediately after this, as long as these 10 assumptions are assumed, then the model would be called classical linear regression model. Okay, so let us quickly discuss these 10 assumptions with as time as possible. The first assumption is about the linearity of the parameters that we have already discussed in one of our previous class. The first assumption is that the model is linear in the parameters. If you remember from our previous discussion, linearity in the sense of regression model actually requires that every parameter in our model, like every beta in our model, occurs with a power of 1. Okay, whether x, the explanatory variable, also comes with a power of 1 or not, it's not the requirement. Although if it is also with 1, that would make your model a little bit easier or simple. But the requirement is, for as the word linear regression model is concerned, it is only for the parameters. So the first assumption says that the model should be linear in parameters. Every beta in your model should be occurring with a power of 1. If it is not the case, then you will be calling it non-linear regression model. The second assumption is that X values are fixed in repeated sampling. Okay. X values means the values of the explanatory variable X, right? This is something that I have already, which means technically we say that X is to be non-stochastic or non-random. And in the last lecture, I have told you that always keep this table in mind, which I call table 2.1, which represents a hypothetical population. And if you look at the values of X here, right, $80 per week, $100 per week, $120 per week, up to $260 per week, we say that this data was generated in such a way that X was, the values of X were predetermined, which means these levels like $80, $100, $120 were predetermined. They were not taken randomly. They were decided, for example, by the investigator in advance. And corresponding to these pre-chosen levels of the values of the independent variable X, the corresponding values of Y were then randomly determined, right? So therefore, X is considered to be a fixed variable. I hope you recall from one of my previous lecture when I said that X is fixed and Y is random. By that, we mean that the explanatory variable in our model is considered to be a fixed variable. It is a variable because it has got different values, but it is not a random variable. A random variable would be that variable whose values cannot be determined in advance. Like, for example, once you consider an income level of $80 per week, then you ask families corresponding to this level of income, what is their weekly consumption expenditure? So these 5 numbers that you see corresponding to X equal to 80, they are then randomly given by those 5 families, right? 55, 60. So in this sense, we say the Y variable is random, while the X variable is fixed. So the assumption number 2 is actually saying that the explanatory variable X and later on explanatory variables, which means more than one X variable. Whether it's one X variable in our model or whether it's more than one, we say that it is a fixed variable. Its values are fixed in advance. They are determined in a predetermined fashion, right? So this is actually assumption number 2. Assumption number 3 is saying that
सर ये assumption number 2 का थोड़ा सा practical example दे जरा kindly.
Assumption number 2. Assumption number 2. I was actually. This is like, for example, I think. हो सकता है मैंने पहले भी दिया हो, but I would just repeat so that if you don't remember, you just recall what I had earlier said. Imagine that you want to collect data from families. I mean, I'm just explaining in the context of the table that you see on the screen right now. So imagine that you want to collect data on these two variables. One is your Y variable, weekly family consumption expenditure, which is your dependent variable of interest, and X is representing weekly family income, okay? So there are two ways of generating data on these two variables. One way would be the most straightforward way, like for example, you just ask two questions from each and every family in your study. Like for example, what you just ask them, what is your income? And question number 2, what is your consumption expenditure? So in this case, every family is totally free to give you any information regarding their income and regarding their consumption expenditure. So in that sense, we would say that both Y and X are random variables, okay? Why they are random variables? Because they can just take any value. I mean, a particular family can give any answer to the X information, and they can give any answer to the Y information. So it's totally up to them to give you a particular information. So in that sense, we would say both the variables are random variables. But for example, if you change your study design in such a way, you say, no, I am not asking, in a sense, information about their income. I have fixed income at 10 different levels in advance. I have designed my study in such a way that I have chosen 10 different income levels, which you can see here on the screen, like $80 per week, $100 per week, and so on. And then you say that corresponding to these 10 chosen levels of income, I will be then considering information from families regarding their consumption expenditure. So for example, if you look at the figure 80, the first column in this particular table, and you just look at the corresponding 5 values, this would be a situation like, for example, you ask a particular family whether your income is $80 per week or $100 per week. I mean, you're just saying first tick one of these levels. If the family, for example, tick $80 per week, which you have fixed in advance, right? Then you ask that family, okay, if you belong to the $80 per income, if you belong to this group, then tell me what is your consumption expenditure. And for example, one family says, my family consumption expenditure is $55 per week. Another family is reporting $60, another one $65, and so on. So if you don't allow X to be randomly reported, rather you say, no, I have chosen X in a predetermined fashion, which means I have chosen the different values of X in advance, and corresponding to these chosen levels of the X values, I would be then determining the corresponding values of Y. So if you do it in this way, then you would say that X is fixed while Y is random. Regression theory basically assumes that you collect data from your concerned respondents, for example, in this way, right? You don't leave X as random. You fix the different levels, the different values of X in advance, okay? And then you collect the values of y randomly, right? So this is actually assumption number 2. Although keep in mind that it's not necessary that x is always fixed in real life, but what I have just said, that you don't question these assumptions right at the start, because as I will be able to tell you what would be the advantage if you keep x fixed and leave the y as random, okay? Because there are certain results which would be possible only if x is assumed to be a fixed variable. Later on, I will be able to tell you that under certain conditions, x can also be a random variable. But this is as far as the meaning of the fixed. This is like, for example, when you are collecting data using a questionnaire, okay? I hope this will also make it clear if the previous discussion were not enough. You want to collect data through a questionnaire, then I hope some of you have already gone through this experience. You can ask questions in the questionnaire using structured questionnaire, or you can also use unstructured questionnaire, or you can use a mixture of that, right? You know what I mean by a structured question. A structured question in my questionnaire would be that in which I just ask a question and then I give different possible answers. And the respondent is just required to tick one of the possible answer which he or she considers to be appropriate in his or her case. So if the possible answers to a questions are already given in the form of different categories and the respondent is required just to tick one of them, this is what we call like fixing that particular variable. But for example, if I ask the question and then I leave a blank line in my question and the respondent is given the total freedom to give any possible answer, then I would say that in this case, I have not fixed the values of my variable, right? In this case, the values of variable are totally random. So this is actually what this assumption number 2 is saying, that you should fix the values of x, but not the value of y. Is it okay for the time being? If it is enough up to this point?
Yes, sir. Thank you, sir. Clear.
फिलहाल अगर और ज़्यादा नहीं है तो आप इसको just take it for granted, right? My typical word is take it for granted, even if it is not clear, because as we move forward, some of the discussions would become even further clear, right? बाज़ औक़ात एक setting में सब कुछ clear नहीं होता ना, so don't worry. Okay. So this is assumption number 2. For some of the assumptions, I would be constantly referring you to this particular table that you can see on the screen right now. Why? Because it would become easier to consider or to understand by considering this table. Okay. If I go to assumption number 3, I would come back to this table because it would be easy to explain assumption number 3, assumption number 4 in the context of this table. Okay. So what is assumption number 3? Assumption number 3 says that the mean of the disturbance term, the mean of the disturbance term, the mean of the error term would be 0. Okay. Expected value of UI, I have already told you that this capital E, which represents expected value, this is simply representing the population mean of a random variable. So this is saying that expected value of UI given xi, this slash actually represents a condition, should be equal to 0. What does it mean? That the mean value of the disturbance term should be equal to 0. If you recall from our previous discussion, I hope I can just show you if I can quickly go back. It's not here. Okay, let me open up the corresponding file which I used in one of the previous discussions. And then I'll be able to tell you something about this. Okay, right. Was it chapter 2 or chapter 3, I think? Yeah, here. If you recall the basic definition of the population regression function, PRF. Okay? PRF. This is PRF, expected value of y given xi. In the context of this table, I had told you that PRF basically tells you how this conditional mean, expected value of y given x, which means expected value, mean expenditure. If x is equal to 80, it is 65. Mean expenditure, if x is equal to 100, it is 77, and so on. So how this conditional mean of the y is connected with x, right? So PRF is basically a mathematical function which connects the last row of this table with the top row of this table, which means connecting conditional mean to the exponential variable x, right? And mathematically, we write it like this, okay? That expected value of y given xi is f of xi, okay? And then in the given case, we say that this f of xi is considered to be okay, right. So this conditional mean of y, this is actually equal to beta 1 plus beta 2 xi. In the given case, f of x is basically the equation of a straight line. So in the simple regression model, this particular part, right. For example, if you just look at this portion, beta 1 plus beta 2 xi, this portion represents if I can just write it like this, like, for example, if I can write down yi equal to this beta naught plus beta 1 xi and plus ui, this one, okay? This is, for example, my model. So this portion, this part is basically representing the conditional mean, okay? This is actually y given xi. And plus ui. So if I want to get this ui, disturbance term, this one, okay? So I have to bring this thing on the other side, over here, okay? So, for example, yi minus this conditional mean, okay? Yi minus this conditional mean, for example, like this, xi. This would be equal to the value of the disturbance term, ui. So this particular thing that you can see right now, this actually tells you how can you get the numeric values of the disturbance term. So the disturbance term is simply the difference between the observed values of the y in the population minus the conditional mean of the y corresponding to a given x, okay, conditional mean of y. So this is actually the in a sense the values of the disturbance term. So if you want to get ui, right? If you want to get ui, then you have to bring all this thing on the other side and you will get that thing. Practically, it means practically this means that if I just come back over here and I want to explain the meaning of this particular assumption, this actually means that somehow if I can get the numeric values of the disturbance term, then this assumption is saying that the mean of the disturbance term corresponding to a given x value should be equal to 0, which means the zero mean of the disturbance term. Now, if I come back to this particular table, I have just told you this result, okay? That disturbance term is simply the difference between an observed y value and the conditional mean of y corresponding to a given x, okay? This means that if I want to get disturbance term values from this table, right? So the disturbance term values will be computed corresponding to a given x values. So for example, if I concentrate on this particular column, okay, right? If I concentrate on this particular column here, okay. If I just look and concentrate over here, so corresponding to this x value, corresponding to x equal to 80, if I want to get the disturbance term values, right? So for example, if I want to get here ui, right, given x equal to 80, okay. So how can I get the ui values corresponding to x equal to 80? It's very simple. By definition, ui is simply the difference between the observed y values corresponding to x equal to 80. What are the observed y values corresponding to x equal to 80? Okay, these 5 numbers that you can see here: 55, 60, 65, 70, and 75. And what is the mean, conditional mean, corresponding to the y values corresponding to x equal to 80? The mean of these 5 numbers corresponding to x equal to 80 is 65. So the difference of each of these y values from this mean 65 will give you the disturbance term value. So for example, the first values of the disturbance term corresponding to x equal to 80 would be obtained as 55 minus 65, okay? The second value would be 60 minus 65. The third would be 65 minus 65, and so on. So if I do it like that, I would just get it like this, okay? So for example, if I want to get the ui values, okay, given x equal to 80, x equal to 80, okay? So the first number would be 55 minus 65. it would be 55 minus 65. Okay, this is not working properly, sorry. So 55 minus 65, what you will get? Minus 10. 60 minus 65, you will get minus 5. 65 minus 65, you will get 0. 70 minus 65, you will get plus 5. And 75 minus 65, you will get plus 10. So the UI values corresponding to x equal to 80 would be obtained by subtracting this 65 from each of these 5 numbers. The resultant figures that you will get, right? Minus 5 here, plus, minus 10 here, 0 here, plus 5 here, and plus 10 over here. If you want to get the mean of those 5 values of the UI, right? If you add them up and divide by 5, what you will get? 0. So the mean of the disturbance term corresponding to x equal to 80 would be 0. Similarly, if you repeat the same process here, okay? If you just do the same process here, if you obtain the disturbance term values corresponding to this x equal to 100, okay? Now repeat the same process for x equal to 100. So corresponding to x equal to 100, if you obtain the difference of each of these numbers, okay, from 77, 65 minus 77, 70 minus 77, 74 minus 77, and so on. So if you obtain the difference of each of these 6 numbers corresponding to x equal to 100 from the conditional mean 77, you will get 6 different values of the disturbance term, right? So you would get, in a sense, these 6 y values will be replaced by ui, okay, corresponding to x equal to 100. X equal to 100. So ui given x equal to 100 would be obtained if you replace these 6 numbers by the numeric values of the disturbance term, okay? And as I have said, how can you get the numeric values of the disturbance term? Obtaining difference of all these 6 numbers from 77. And if you obtain the mean of all those 6 values of the disturbance term, right? Then the assumption says that it should be equal to 0. This is exactly what we mean by this assumption, okay? So this is just the meaning of that the mean value of the disturbance term should be equal to 0. Although there is also a mathematical proof for that, but this was for the time being just a sort of numeric meaning of this. So this is a very important assumption of the regression model, which later on helps a lot in getting different simplified results of a regression model. The 4th assumption of the regression model is that of homocydasticity, right? Or equal variance of the disturbance term, or sometimes called, this assumption is also called the assumption of constant variance of the disturbance term. Given the value of x, the variance of the disturbance term is same for all observations. Symbolically, we say that variance of ui given xi, right? Variance of the disturbance term, variance of all those disturbance term values corresponding to a given x, right? This should be equal to a constant, and in econometrics, we represent this constant variance by a symbol that we call sigma square. This is a lowercase Greek letter sigma and then square, so we call it sigma square, right? So this says that the variance of disturbance term corresponding to a given x value would be equal to a constant number sigma square, and it would not change if you go from one x value to another. What is the practical meaning of this? I have described the meaning of zero mean just immediately before this, where I said that if you convert y values corresponding to each of x values into disturbance term, like for example, obtain 5 different disturbance term values corresponding to x equal to 80, then obtain the disturbance term values corresponding to x equal to 100, and similarly obtain the disturbance term values corresponding to x equal to 120, okay? And how you get it? Simply obtain the difference of these y values from the corresponding conditional mean in the last row, okay? So, in a sense, if you convert all these y values corresponding to x equal to 80, y values corresponding to x equal to 100, if you convert all these with the disturbance term values using the definition of disturbance term that I have just described here, okay, this definition, okay, the difference between y and conditional mean. If you use this discussion, then the previous assumption was saying that the mean of all those disturbance term values should be 0. This assumption of constant variance is saying that the variance of the disturbance term corresponding to x equal to 80, the variance of the disturbance term values corresponding to x equal to 100, the variance of the disturbance term values corresponding to x equal to 120, and so on, all these should be exactly one and the same. So the variance would not change when you change from one x value to another x value, right? This is actually what we call the assumption of constant variance. We would have a separate lecture on the violation of this assumption. Violation of this assumption means that what if this variance, which we are assuming here to be constant, what if this is not constant, okay? What if it is non-constant? By non-constant, I mean, what if the variance of the disturbance term values corresponding to x equal to 80 is one number, and that corresponding to x equal to 100 is another number, right? The assumption of constant variance says that if the variance of the disturbance term values corresponding to x equal to 80 is 25, for example, okay, imagine any number, let's say 25, then the variance of the disturbance term values corresponding to x equal to 100 should also be 25. And it should also be 25 corresponding to x equal to 120, 140, 160, and so on. So as you move, in a sense, as the x values increases from 80 to further higher numbers, the variance of the disturbance term would not change. Later on, we would see that there are many practical examples in real life where this assumption would be violated, which means where this variance would not be constant. And then we will be talking about the violation of homocydasticity, right? Homo stands for same, cydasticity stands for spread or variation. So when we say homocydasticity, we are saying that same variation or constant variation, okay? Or in a sense, same variance across all values of x. So the opposite of homocydasticity is heterozygosity, okay? So we replace the word homo by hetero. And you will see from our discussion over there, like for example, in how can we imagine a constant variance situation in real life, and how can we talk about the violation of this thing? But as I said, that for the time being, we are not talking about or questioning how it is possible that the variance would remain same from one x value to another, because the assumption says that it should not change. And you will see that this would also be quite helpful in getting fundamental results of regression models. Okay, graphically, it means something like this. Constant variance actually means that the distribution of all x values, of all values corresponding to the first value of x, and the distribution of all values corresponding to the second values of x, third values of x, and so on. As you can see, the shape of this distribution remains the same, which means that there is no variation. Okay, the variation, the spread remains the same. This is actually what we call homocydasticity. But if you have something like this, as you can see here, now if you look at this one, the variations in the distribution of values corresponding to the first value of x, like x equal to 80, here variation is comparatively smaller, because when the two tails of the distribution, when the two tails of the curve are closer to each other, then we say that there is less variation. As the two tails become flatter and flatter, as you can see here, we say that now there are more variations in our data set. So this is a case of increasing of variation, larger variation. When at lower values of x, variation is smaller, and as you move to a much larger values of x, variation is increasing, right? This case will be later on given the name of heterozygosity. Heterozygosity is a very important aspect of a econometric model. When we will be considering this particular topic in one of the lecture, there I will tell you what is heterozygosity, why it is important to study this heterozygosity, what would happen to your model if the assumption of constant variance, homocydasticity, is not holding, and how can you correct your model? I mean, if you are convinced that heterozygosity is going to damage your model, then what would be the remedy? How can you make sure that this heterozygosity, this violation of constant assumption, is not going to damage the basic properties of your model? So that could be actually left to one of the other lectures. But for the time being, we are assuming a situation like this, and we are saying that we don't have a situation like this, right? Till the point where I would be able to tell you that it's not necessary that in real life we always have the constant variance situation, right? So initially we assume homocydasticity, constant variance, and then at some later stage we say, what if there is heterozygosity? What if there is no constant variance? What if the variation is increasing or decreasing? So what should you do then? Okay, the next one is assumption number 5 says that there should be no autocorrelation between the disturbances. Between the disturbances means between the different values of the disturbance term. Symbolically, we just use this particular thing, that the covariance of the ith value of the disturbance term and the jth value of the disturbance term should be 0. Remember, covariance is the rough form of correlation. A common man is more familiar with correlation, okay? But covariance is the initial form of correlation. We say correlation is a standardized form correlation is a standardized form of covariance. Covariance is basically a measure of joint variation. In simple possible word, this assumption is saying that the correlation between different values of the disturbance term should be 0, right? There should be no overlap between different values of the disturbance term. But if this assumption is actually violated later on, if there is a correlation between different values of the disturbance term, then we say that this is a problem of what we call autocorrelation. So you are all familiar with the word correlation. The only thing which may not be that much familiar to some of the scholars is the word auto with the word correlation. So it would become quite clear when we will be considering this topic in much more detail. There I would be able to tell you, for example, what is autocorrelation and why it's a problem for a econometric model. More importantly, how can you know that there is this problem, autocorrelation, in your model? And lastly, how can you correct your model for autocorrelation? But autocorrelation, which is a special type of correlation, This assumption number 5 is saying that there should be no autocorrelation in your model, which means no two values of the disturbance term should be correlated with each other. This is also a simplifying assumption. Under this assumption, the initial standard results of the econometric model are actually achieved. Okay, this is just a graphical way of saying that thing. This last figure is actually telling you that there is no correlation between two different values of the disturbance term, while the first figure is telling you that there is a linear positive correlation, and the second figure is telling you that there is a linear negative correlation. Okay. For the time being, you can say that, for example, consider different values of a disturbance term and see whether there is correlation or whether there is no correlation. If there is correlation, we would say that this is what we call autocorrelation. But if there is something like this, then we say there is no autocorrelation. So regression model initially assumes that there is no case of correlation in the values of the disturbance term. So you have a figure like this, right? Later on, we would see what if this is not the case, then what should you do with your econometric model. Assumption number 6 is also a very important assumption of regression model. This says that there should be zero covariance between the disturbance term and the explanatory variable, or in a more layman language, we say that there should be no correlation between the disturbance term and the explanatory variable x. Okay, covariance of ui and xi should be zero. Actually, it means that the correlation between disturbance term and the explanatory variable should be zero. What is the practical meaning of this? The practical meaning of this is that if you have a model, like for example, if you have this model, okay, if you have a regression model involving, for example, simple one x variable for the time being, okay, so imagine that you have a model like this. Okay, so this is y variable, and then you have this beta naught plus beta 1 and plus ui. So this assumption is actually telling you something about the variable x in your model and the disturbance term u. Okay, if you recall our previous discussion, x is what we call the included explanatory variable, right? X is the explanatory variable included in our model, while ui is a common basket, which in a sense represents all those excluded independent variables, all those known or unknown factors. So when you say that the correlation, right, the correlation between ui, okay, and xi is zero, what you are trying to say? You are trying to say that x has nothing in common with ui, because ui in a sense represent all those other possible independent variables. So when you say that the correlation between them is 0, you are saying that there is no overlap between x and ui. There is no overlap between x and all those other explanatory variables. In a sense, you are saying that whatever information x is giving you regarding the y variable, and what is that information? Remember, the effect of x on y is given by this particular term, right? Beta 1. Beta 1 is basically telling you how much x affects y. So this assumption is saying that the information in the form of beta 1 that you are getting, okay, information that you are getting in terms of beta 1 regarding the effect of x on y, this is not shared with any other x variable in your model. So in a sense, x is telling you, in a sense, all it can regarding the behavior of y. And no information about the effect of x is actually shared with any other x variable which is part of the disturbance term, right? So what you are getting,
एक्सक्यूज मी सर
yeah,
सर इसका मतलब ये है कि जो हमारे एक्सप्लेनेटरी वेरिएबल x है उसमें सर मल्टी कोलिनिटी सर नहीं है.
no, I'm not talking about multi-corinality. Okay, this is something towards which I would come in a moment. This is something different than multi-corinality. Okay, let me explain again what I have just said. This assumption that we are talking about, which says that the correlation between x and ui should be 0, this is saying that there should be no correlation between the included independent variable and those which are not included, but they are part of the UI. So here we are not talking about any other explanatory variable in our model. Here we are only talking about the one which is included and all those others which are excluded. So it is telling you that whatever x variable you have included in your model, that is in a sense giving you the true effect of that variable on y. If this x variable is somehow correlated with some of the variables in the disturbance term, then you would not be very sure whether beta 1 is giving you the true effect of x on y or not. Okay, so here we are only talking about the effect of the included x variable, which is not shared with any of the variable which is not included in the model. So we are only talking about the x variable and the disturbance term. Remember, disturbance term represents excluded variable. Okay, so multi-corinality is something else. So अभी मैं आपको इसके बाद बताने वाला हूँ, which would be a little bit different from what I'm just saying. So this assumption is sometimes also called assumption of exogeneity, right? We say that if this assumption is holding, like for example, if the correlation between disturbance term and x is 0, then we say that actually x is an exogenous variable. Okay, x is an exogenous variable. If this assumption is violated later on, for example, we have something like this. If the correlation between ui and xi is not equal to 0, what it would mean? It would mean that there is or there are some other explanatory variables which are part of the disturbance term, which have some correlation with the included variable x. And due to that, the beta 1 is not giving you the true effect of x on y. Some effect is given, but some of them is shared with some of the other variables, right? If this is the case, like for example, if correlation between disturbance term and the independent variable is not equal to 0, right? Then in econometric terminology, we call it the assumption of endogeneity, right? Endogeneity, right? So therefore, we can also say that this assumption number 6, is actually called the exemption of exogeneity in the model. Like X should not give you something which is common with disturbance term. And if this assumption is violated, if this later on is considered to be not holding, then we would say that there is endogeneity in our model, which means that X is not exogenous, it is basically endogenous. But initially we say that there is no problem and this assumption is holding, right? Initially for getting some standard results of our regression model, we assume that the correlation between disturbance term and the X variable is 0. Assumption up to assumption number 6, they are a little bit technical assumptions, but beyond that, the assumptions are comparatively straightforward. Like for example, assumption number 7 is saying that the number of observations, which means the sample size, which you are using for your data on those variables, the number of observations n must be greater than the number of parameters to be estimated. Or alternatively, the number of observations n must be greater than the number of explanatory variables in your model. So this assumption is simply saying that the sample size that you are using for your data should be greater than the number of parameters to be estimated. Like in simple regression model, there are 2 parameters that you are estimating, okay? One is beta naught, the other one is beta 1. So according to this assumption, your sample size must be greater than 2. It should not be 2 or less than 2. Although initially it would seem quite strange, but I mean, if your model becomes very large, like rather than just one X variable in your model, imagine that you have 10 variables in your model, 10 X variables, or you have 20 explanatory variables in your model. So if there are 20 explanatory variables in your model, so how many betas would be there? Anyone? If there are 20 X variables in your model, okay?
There would be 21 betas, I think.
Exactly. Because we know that the number of betas are always one more than the number of X variables. As you can see here,
Yes, sir.
the number of X variable is 1. So the number of betas are 2 because of this intercept beta naught. So you can imagine that if we include one more X variable, like for example, if we say Y is equal to, let's say, beta naught. Sorry. So Y is equal to, let's say, beta naught plus just leave it for the time being. But if you increase the number of betas in the model, then naturally if you increase the number of X variables in your model, then the number of betas would also increase. So the general rule is that the number of parameters, the number of betas in your model would always be one more than the number of X variables. So if there are K explanatory variables in your model, then the number of parameters would be K plus 1. Like for example, if there are 20 explanatory variables in your model, then the number of parameters, betas, would be one more, 21. So this assumption is saying that the number of observations in your model must always be greater than the number of parameters, or in that sense, the number of variables in your model. So if you are dealing with a much larger model later on, then this assumption becomes quite crucial, right? In simple regression model or a model with just 2 explanatory variables, this is not really a big problem because your sample size would always be larger. But as your model becomes larger and larger in terms of the number of explanatory variables, then this assumption says that your sample size must not be smaller than, like for example, if the number of explanatory variables in your model are 20, and if your sample size is 15, you will see that you will be facing estimation problems. You will not be able to estimate some of the parameters of your model. So therefore, your sample size must be sufficiently large, and the minimum sufficiently large meaning is that it should be larger than the number of parameters. Assumption number 8 is also very straightforward, like there should be variability in X values, which means that X values should not all be the same, okay? Like for example, you should not have data in your sample, or in, for example, you should not take data from families who are earning only $80 per week, because in that case, the X values would all be 80, 80, 80, and so on, and there would be no variability in the X values later on, right? And this will affect most of the calculations that you will do for your model. So therefore, as you can see here, although X is fixed, but it is not, in a sense, taking all the same values, because some of the families are earning $80 per week, while some of the other families are earning $100 per week, and so on and so forth. So this is called that there should be variability. X values should not all be the same. It should be, which is of course a very straightforward sort of thing. But later on, I would show that if this assumption is not taken care of, what would be the problem that you would face in your estimation and calculation of econometric model. Assumption number 9, regression model should be correctly specified. Alternatively, there should be no specification bias or error in the model used in the analysis. Specification of the model actually means that what should be the f of x that you consider for your model, right? For example, when we were considering the PRF, population regression function, so we say the right-hand side should be a function of the explanatory variable, or later on, function of explanatory variables like x1, x2, and so on. So which function of the explanatory variable you should consider, right? Should it be, for example, should it be linear or non-linear? Should it contain just one x variable or more than one x variable? Okay, etc., etc. So this is actually what we call that the regression model should be correctly specified, right? Let me tell you that this assumption number 9 is the most difficult assumption in econometric model, because apparently a very simple, straightforward thing, but practically it becomes quite difficult to ensure that you have taken a correctly specified model, because you never know whether the model that you have taken is the model that you should have taken or not. Okay, like for example, if you have considered a model with one x variable, maybe there is a model, maybe a model with two explanatory variable should have been taken rather than just one. Maybe you have included, for example, x in your model. Maybe the correct specification required that you should have also included the square of x in your model. Okay. For example, you may have considered the model which is linear also in variables, but maybe the correct specification requires that you should have taken log of x, or you should have taken 1 over x in your model. You should have taken, for example, x square in your model, whatever. So the assumption number 9 says that you should take that particular specification of the model, which is the right specification. But practically, as you know from the discussion that I'm doing, that it becomes quite difficult. You only make your best possible knowledge to decide whether the model that you have taken is in correct specified form or not. So you use idea from the literature, like extensive literature review. You also use your own personal knowledge, discussion with your professor, with your colleagues, and all those things then decide what should be the proper form of your model. Okay, but even if you take all those steps, it would be very hard to say that you would have taken 100% correct specification of the model. So in practice, it would not be that much necessary to make sure that this assumption number 9 is satisfied in its original form. But you would say that if the model that I have considered after thorough consideration from the literature, using my own knowledge, using the guidance from the professor and other co-researchers, if that model is giving you satisfactory results according to the different standards that you will learn in this course, then you would say that, okay, it may not be the exact correct specified form of the model which I should have used, but because this model is giving me satisfactory results, so therefore I would still be okay with this model, even if I don't know whether this is the model that I should have used or not. But if the model, in a sense, satisfies some of the requirements of a good model, then you should be happy with that. The last assumption is the assumption of no perfect multicoordinality. Okay, no perfect multicoordinality. Here comes the difference with the assumption that I had considered previously. When we talk about just a minute. Just 2 seconds. Okay. Assumption number 10 is talking about the existence of correlation. Existence of correlation among different values of the explanatory variables. One thing that I should quickly clarify over here, in comparison to the last 9 assumptions, this assumption number 10 is talking about a multiple regression model. Okay, so assumption number 10 would not make any sense if you are dealing with a simple regression model, which means if there is only one x variable in your model, then forget about this assumption number 10. But if there are 2 or more explanatory variables in your model, like for example, you have x1, x2, x3, x4, and so on in your model, then this assumption number 10 is saying that there should be no perfect multicorinality in your model. Although multicorinality is a topic that I would discuss in detail in one of the next lectures, but for the time being, to give you a quick idea what we mean by this, multicorinality refers to the existence of correlation between or among explanatory variables in a regression model. Okay, so if there are 2 or more explanatory variables in your model, then the correlation between any 2 of them is referred to as collinearity, right? And multicollinearity means that more than 2 explanatory variables can be correlated with each other. So this assumption is not saying that there should be no correlation. As I would explain in the appropriate lecture on multicollinearity, ideally, no explanatory variable in your model should be correlated with another explanatory variable in your model. Keep in mind that here I'm talking about the included explanatory variables. When I was talking about the assumption of exogeneity, there I was saying that there is one variable x which is included in the model, and then there are other explanatory variables which are not included, right? And you are talking about the correlation between the included and the excluded. Here I'm only talking about the correlation between or among the included explanatory variables. So keep in mind that I'm saying that suppose there are 2 or more x variables in your model, then multicollinearity refers to the correlation between or among those explanatory variables. So this assumption is saying that there should be no perfect multicollinearity. Okay, by perfect multicollinearity we mean that there should be no perfect correlation between any 2 explanatory variables in your model. Yes?
Sir, sir, if there is multi-collinearity, then what is the solution? How we remove it?
Yeah, so this is exactly what I'm saying, that because for the time being, I'm only introducing the idea, there will be a full, in a sense, lecture on the phenomena of multicorinality, and there we would discuss every aspect of multicorinality in much detail, okay? For example, I would tell you what is multicorinality, why it's a problem, what is the effect of this particular problem on your econometric model, how can you know that there is multicorinality in your model, and lastly, how can you correct your model for the bad effects of multicorinality. So you have to wait for maybe 1 or 2 lectures before we can just go into the detail of this. Right now, I'm not going into the detail of this problem called multicorinality. Right now, we are only saying that the assumption is saying that there should be no case of perfect multicorinality, right? So for the time being, it's okay if you know what we mean by multicorinality and what we mean by perfect multicorinality, okay? Multicorinality means correlation, the existence of correlation in the explanatory variables in your model. Perfect multicorinality means the existence of perfect correlation. I hope you know what when I use the word perfect correlation, right? If the correlation between any 2 variables is exactly +1 or -1, then we say that this is called perfect correlation. In a layman language, perfect correlation means that if one variable increases by 1 unit, and in response to that, the other variable is also increasing exactly by 1 unit, then this is called perfect correlation, right? But if one variable is increasing by 1 unit, and the other variable is also increasing or decreasing, but not exactly the same quantity, then we say that there is less than perfect correlation, right? So perfect correlation is the strongest possible correlation that you can think about. So therefore, this assumption is only saying that the case of perfect correlation should not be there, okay? The case of perfect correlation should not be there. When I will be introducing the idea of multicorinality in econometric models, there I will tell you what would happen if there is a case of perfect correlation in any 2 explanatory variables, right? Why it should not be there. So therefore, this assumption is actually talking about the absence of perfect multicorinality, okay? Ideally, there should be no correlation between any 2 explanatory variables in our model, but practically it's not possible, which I would explain later. But as I have told you, this assumption number 10 is valid only if the number of explanatory variables in your model are more than 1. As long as there is 1 x variable in your model, there is no concept of correlation, right? And therefore, there is no problem of perfect multicorinality. But assumption number 1 to 9 are valid irrespective of the number of explanatory variables in your model. चाहे एक x variable है, चाहे एक से ज़्यादा है, this would actually be the case. So these are 10 assumptions which we consider in case of classical linear regression model. Okay. And one last thing before I can move to the next topic is a very important theorem. Although we are not, in a sense, going to go for the proof of this theorem, but because this is a very important result in the context of the OLS method, so I should quickly tell you the meaning of this Gauss-Markov theorem. And this, in a sense, will also tell you that why this OLS method is considered to be so important method in regression modeling. Gauss-Markov theorem, which is named after 2 mathematicians, a German mathematician Gauss and a Russian mathematician Markov, it is simply saying that given the assumptions of the classical linear regression model, I mean, given those 10 assumptions that we have just described, the least square estimators or the OLS estimators in the class of all unbiased linear estimators have minimum variance, that is, they are blue. Let me tell you what is the meaning of this. It is actually saying that if you obtain the estimators, if you obtain the estimates of your parameters using the OLS method, then these estimators would possess three important properties which would make it different from any other estimator for your parameter. These three properties are linearity. We say that these would be linear estimators. Unbiasedness, that we say that these estimators would be unbiased. And minimum variance, which is called the best. So under these assumptions, the OLS estimators are considered to be best linear unbiased estimators. Okay, linear in the sense that these parameters would be linear. They would be linear function of the dependent variable y. Unbiased actually means that on the average, they will give you the parameters. The average value of the estimators would be actually equal to the parameter. And best, which refers to the minimum variance property, it is actually saying that if you obtain estimators of your parameters by any other method other than OLS, and suppose that those estimators also possess the other two properties, like they are also unbiased and they are also linear, but OLS estimators would still be preferred because the variance of the OLS estimators would be the minimum of all, right? So in a nutshell, when we talk about the blue property of the OLS estimators, we are saying that OLS estimators possess the minimum variance among a class of all unbiased and linear estimators of the parameters. So what I just wanted to say is like this, that blue property, best linear unbiasedness property, is a single most strongest reason why OLS method is such a preferred method in regression theory, right? So just as a matter of general knowledge, if you want to know why we go for the OLS method rather than other methods, then one of the reasons is this blue property, because the estimators obtained through this method would possess these three important properties: linearity property, unbiasedness property, and the minimum variance property. That's why we call them blue, best linear unbiased estimators. Okay, this was some of the discussion related with that. Had we discussed the idea of R square in one of our previous lectures or not?
No, sir.
Okay. One quick
No, sir.
one quick discussion of this R square. When you fit a model, like for example, in the last lecture, we fitted a simple regression model. We also used the software Stata for that. One immediate question would be to know how good this model is, how much good or bad your fitted model is, right? And one of the measure of the goodness of fit is to determine how much the included explanatory variable is telling you about the variable of interest that you call dependent variable, right? How much X explains Y. If X is independent variable and Y is a symbol for the dependent variable, then one way of determining whether you have a good model or a bad model is to determine how much the included explanatory variable X is able to tell you about the dependent variable Y. The more it tells you about Y, the better your model would be. The less it tells you about Y, the poor your model would be, right? So a measure of goodness of fit for that purpose is what we call the coefficient of determination. coefficient of determination, which is represented by R square. Okay. Usually we use the capital R square notation for that. This is a summary measure that tells how well the sample regression line fits the data. In other words, how much the X is able to tell you about Y. And later on, how much the X1, X2, and so on that you have included in your model are able to tell you about Y. Right? So the formula for R square is something like this. The total variations in the values of the Y variable, the dependent variable, is measured by a formula that we write like this, right? If you look on the screen at this particular formula, sigma Y minus Y bar whole square, this sum of square is used to measure the total variations in the values of the dependent variable Y. What does this measures? When you say yi minus y bar, which means you obtain the mean of the y values and you subtract this mean from each and every y value, and then you take the square of such differences. So the sum of these square differences, the sum of square differences from the mean of y, is what we call representing the total variations of the actual y values. Okay. A more appropriate terminology for this is what we call the TSS, total sum of squares. So TSS, which is represented by this formula, summation yi minus y bar, if the deviation, if the difference yi minus y bar is represented by small y, then summation small yi square is the same as this, right? So whether you write it in this form or in this complete form, it doesn't make any difference. But we call this particular quantity, this sum of square, we call it the TSS. So TSS is a measure of determining the total variations in the values of the dependent variable y. And then we can split this TSS into two parts. Okay. Mathematically, we can show that this TSS can be divided into two parts. As you can see here on the screen, although the derivation for the time being is not that much important, but we can show that this summation yi square, small yi square, can be divided into these two parts. If you look at the second part, summation ui hat square, this is what we call the residual sum of square that we have used in the OLS method, right? While the first part is what we call the explained sum of square or the regression sum of square and so on. So practically, we have a sum of square identity, which we write it like this. We said that TSS, the total variations in the values of the dependent variable y, can be split into two parts. One part is called ESS, explained sum of square, and the other part is what we call the RSS, residual sum of square. In simple layman language, we say that the variations occurring in the values of the dependent variables y can be divided into two parts in such a way that some portions of the variations in y will be such that the independent variable x will be able to explain. Like, for example, if y is consumption expenditure and x is income, then we say that some variations in the consumption behavior which are occurring would be due to income. If income increases or decreases, it would have some impact on the consumption behavior. But we know that income is not the only factor which brings variations in consumption behavior. There are so many others. So this residual in a sense, represent the remaining factors other than income. So when you say TSS can be written as ESS, ESS stands for explained sum of square, right? And RSS stands for residual sum of square. So ESS represents that portion of the total variations in the values of the dependent variable y, which the explanatory variable is able to explain. While whatever the explanatory variable cannot explain, that is what we call is the unexplained. Unexplained means those which are due to the factors which are for the time being not part of the model. So R square by definition is simply the ratio of explained sum of square to the total sum of square. Although there is formula for ESS and there is a formula for TSS, but if you focus for the time being on this ratio, ESS divided by TSS. ESS represent the portion of total variation of y which is explained by x. So in common language, we say R square is the ratio of explained variation to the total variation. You can also write down the numerator as explained variation, those which are explained by x, for which we have a formula, and divided by total variation. So as you can see here, because this explained variation ESS is part of TSS, I have already shown that TSS is basically ESS plus RSS. So R square is simply the ratio of ESS to the TSS, right? The more this ESS is, the more would be the value of R square. The smaller this ESS is, the smaller would be the value of R square. So therefore, we say that a higher R square would mean that the included X variable is able to explain more. The smaller. Alternately, there is also an alternate formula for R square, which says that R square can also be obtained as 1 minus residual sum of square divided by total sum of square. Or you can say 1 minus unexplained variation divided by total variation. But the numeric answer to these two would be exactly one and the same. Practically, the value of R square is always between 0 and 1. When R square is 0, it means that the X variable in our model is explaining 0 variations in Y, which means that X is not telling you anything about Y. When R square is 1, it means that everything in Y is explained by X. So X is telling you everything about the Y variable, right? For a layman, usually we multiply the value of R square with 100, and then we say how much percent of the total variation in Y is explained by X, right? So if you look at the results that we had considered in our previous discussion, like for example, in our previous lecture, we took this data and we used data to obtain our results, okay? And the R square that we got over there was 0.9621. As you can see here, this number that we call R square, the coefficient of determination, is between 0 and 1. It is very much closer to 1. So the closer it is to 1, the better situation it represents. So how can you explain the meaning of this number? Technically, it means that 0.96 fraction of the variation in Y is explained by X. But because this is not that much easier language for a layman, so we usually multiply this number with 100 and then try to explain it. So 0.9621 actually means 96.21%. Okay, so you can say that R square is 0.9621, which means that 96.21%, which means approximately 96%. 96.21% of the total variations in Y is explained by X. if Y represents expenditure and X represents income, then the R square 0.9621 actually means that 96.21% of the variations in consumption expenditure is explained by income alone. So this actually shows how much income contributes towards explaining the nature of consumption expenditure, right? If this number is exactly 1, it would mean 100%. If this number is 0, it would mean 0%. Okay. So therefore, we initially require that this R square should be as larger as possible. Okay. As you can see here, yeah. Is there anything you want to ask? G.
सुरमी सर
G.
सर इसमें अगर हमारा जो मॉडल है अगर इसका सपोज आ गया 30% या मिनिमम जो मॉडल का फिटनेस का वो है जो यास्टिक है वो सर क्या होगा?
इनिशियली तो R स्क्वायर आपको समझ आ गई ना कि फॉर एग्जांपल R स्क्वायर क्या रिप्रेजेंट करता है, राइट? So initially you should be very clear.
बिल्कुल सर.
You should be very clear that what are the limits. Numerically तो 0 और 1 के दरमियान है, right? But उसको फिर आप इंटरप्रेट कर सकते हैं. Now the next question is, for example, what should be a reasonable value of R square? ये आपका question है ना? Right?
बिल्कुल सर.
What should be, because this is a natural question. One thing is quite clear, because R square represents how much the included explanatory variable or variables later on. क्योंकि मैं ये कह रहा हूँ फिलहाल मैं एक X variable के sense में बात कर रहा हूँ, but the same interpretation would apply if there are more than one X variable in your model. R square would represent how much the included explanatory variable or variables are contributing towards the dependent variable Y. So one thing is quite clear. The larger the better, the smaller the worse, which means that the closer the value to 0, the bad situation would be. The closer the value to 1, the better it would be. So how much better is better and how much worse is worse? Although later on I can also tell you that you can apply a statistical test of hypothesis to determine whether a given R square value is significant or not. लेकिन फिलहाल हम उसमें चूंकि नहीं जा रहे हैं तो मैं आपको एक जिसको कहते हैं ना कि क्या वो कहते हैं as a matter of convention मैं आपको बता रहा हूँ कि for example what are the practices that people usually do to decide whether this R square is better or not. If R square is less than 0.5, okay, if R square is less than 0.5, इसका मतलब क्या होगा? Practically for a layman it would mean that less than 50% is the contribution of your independent variable. तो एक तो ये एक threshold है कि we would like that our R square should be more than 0.5, number one. ठीक है, यहाँ तक समझ आ गई ना? Okay.
Sir.
Next is when we say that the larger the better, then how much larger is larger? Ideally तो आपके पास इसकी value 1 होनी चाहिए, यानी 100%. Then there are some practices. But remember when we say something like convention, so when as a matter of convention जब आप बात करते हैं, so it is just based on traditional approaches which may not be based on any theory. So traditionally we say that the R square value should be more than 0.8, 0.8. Okay, it should be more than 0.8.
80%.
80%.
Sir.
If the R square value is more than 0.8, which means if it is 80% or more, then it would be considered a good number. And if it is more than 0.9, right, like more than 90%, then it would be considered a very good, excellent number. So therefore, 0.8 and 0.9, they are considered to be preferable. But at the same time, it doesn't mean that if your R square becomes smaller than 0.8, then it should represent a bad model. Why? The reason is, कुछ और reasons भी हैं जो मैं आपको बाद में बताऊंगा when we will go for hypothesis testing. क्योंकि ये जो मैं फिलहाल आपको बता रहा हूँ ना, this is what we call subjective approach, right? Subjective approach usually वो होता है जो कि usually practices पर based होता है. Later on, I would also tell you an objective approach, like for example, how can you objectively assess whether a given R square value in your case is a significant value or not a significant value, right? क्योंकि इसमें और बहुत सी चीजें आ जाती हैं, sample size आ जाता है, so on and so forth. But for the time being, I would say that sometimes an R square value smaller than 0.8 can also be acceptable if the researcher can justify that in my model, even an R square value of 0.64, like 64%, is also okay, because researcher के पास argument ये होगा कि because of these particular properties of my model, the model is giving me excellent results, even if the R square is smaller, but because the other results of my model are quite good, they are according to literature, so therefore I can still report this model. So therefore ये आप ध्यान में रखें कि it's not necessary that in order to adopt a model, you should have a very high value of R square. Sometimes a considerably reasonable value of R square is also accepted, depending on how the researcher can defend that thing. But one thing is quite clear, if your R square is less than 0.5, in that case, it would become quite difficult to defend your model, because that means that the included explanatory variables are actually contributing much lesser to your dependent variable as compared to the excluded variable. Okay? उसमें भी कुछ exceptions हैं जो बाद में हम discuss कर सकते हैं कि for example, there are situations when people have reported a model where even the R square is less than 0.5. लेकिन उसके लिए फिर अपनी conditions हैं. So ideally, if your R square value in a given case is 0.8 or more, then you should be really happy to report that thing, right? फिलहाल आप इसको इस तरह ले लें. उसमें कुछ और details हैं कि हम बाद में जाके discuss करेंगे कि for example, how can you objectively assess a given R square value? उसके लिए फिर एक hypothesis test है जो मैं आपको suggest करूँगा, which you can run quite easily, and then you will be quite confident to determine whether a given R square value is okay or not. Because जब हम stata session करेंगे वहाँ पे मैं आपको बताऊँगा कि sometimes the R square value may be smaller, but your model would still be giving you satisfactory results. तो आप model को सिर्फ इस वजह से reject नहीं करेंगे कि because the R square value is smaller, so therefore I'm not using it. Is it okay for the time being?
Thank you, sir.
Yes, sir.
यहाँ तक ठीक है ना?
Yes, sir.
Yes, yes, sir. Yes, sir.
Okay.
Yes, sir.
सर एक्सक्यूज मी सर.
जी जी प्लीज.
सर आज थोड़ा यहाँ से नेट का इशू बहुत ज्यादा था तो बार बार डिस्कनेक्ट होता था ना, तो जहाँ तक नेट ठीक था वहां तक तो सही समझ आ गया ना.
राइट.
जहाँ तक नेट खराब था तो वहां पे कुछ समझ नहीं आया. तो काइंडली सर आप आज अगर ये लेक्चर पॉसिबल हो तो शेयर करें ताकि फिर टाइम नहीं हो तो वीकेंड पे उसको जरा दोबारा.
अभी मैं भेजता हूँ आपको, ठीक है?
ठीक है. थैंक यू सर.
Okay. Unfortunately today we could not go for in a sense more numeric stuff, लेकिन थोड़ा सा ये background information discuss करना जरूरी था. What we will do in the next lecture, we will directly start with the multiple regression model using Stata, and then I will directly start with the discussion of multi-corinality. So multiple regression and multi-corinality would be the topics for our next lecture. Okay. Till then, thank you very much.
Thank you.
Thanks a lot.